Hello students, today's topic is orthonormal basis, and this is one of the topic where the definition could be asked. So please study the definition, and coming to the problems, understanding the term orthonormal basis is very important to solve the problems. All right, so what is orthonormal basis? The definition is the set of vectors, say v1 to vn, in an n-dimensional inner product space is an orthonormal basis if the orthogonality is equal to 0 and normalization is equal to 1. So orthonormal basis is nothing but it is a basis of vector space that is v1 to vn, whose vectors are both orthogonal. What is orthogonal? Is nothing but it is equal to perpendicular. What is normalized? Normalized means they are having the unit length, which is nothing but inner product of vi to vj is equal to 1. Okay, so this is also a concept often used in Euclidean spaces and functional analysis. So let us take one simple example. Say u1 is equal to say 1 by root 2 and 1 by root 2, and u2 say another vector which is having minus 1 by root 2 and 1 by root 2. Okay, now what does orthogonality mean? Orthogonality is you have to find the inner product of vi comma vj should be equal to 0, which is nothing but you're finding the dot, right? So inner product of u1 comma u2 is nothing but you are finding, so you have to take the complement, right? So it is 1 by root 2 and 1 by root. I'm taking the complement of u1. Okay, what is u2? Same, minus 1 by root 2 into 1 by root 2. Now let us multiply. What we will get? 1 by root 2 into minus 1 by root 2 plus 1 by root 2 into 1 by root 2. So the answer will be equal to 0. This is orthogonality. Okay, let me take one more example for orthogonality, but you have to solve it on your own. So let me take say e1. Say e1 is equal to say the vector 1 0 0, and e2 let be one more vector, say 0 1 0, and e3 let it be 0 0 1. Now how will you find the inner product? There are three terms. How will you find? It is inner product of e1 e2, inner product of e1 e3, and inner product of e2 e3. Okay, you have to find on your own. I'm not going to solve this. So tell me what is the answer you are getting. So this is all about orthogonality. Now one more term in orthonormal basis is what? It is nothing but your normalization. How to find the normalization? Normalization's formula is what? It is always the magnitude of something, magnitude of that vector, right? So as we see the the example, so let me take the same example as I've taken for the first one. We have to prove it is equal to 1. Okay, so let me take the first example only. So that is magnitude of u1 is what? It is root of 1 by root 2 the whole square plus 1 by root 2 the whole square. We have done n number of problems on this. So if you solve this, it will get it as 1. Say for u2 also solve for same. So it is minus 1 by root 2 the whole square plus 1 by root 2 the whole square. So you'll get the answer as equal to 1. Now similarly try to solve for say magnitude of e1 e2 and e3. That will be kind of a homework, so please pause the video and do it on your own and check. So this is all about orthonormal basis. The second we'll see about orthonormal complement. So the orthogonal complement is also called as a perp. Oops, I erased it. So it's orthogonal complement. It is also called as perp. It is called as v perp. So if I read it, it is a given subspace V in an inner product space W. The orthogonal complement V perp is defined as V perp is equal to W belongs to W, such that inner product should be equal to 0 for all V belongs to V. Okay, so what we have here, the main thing is we have to find the dot products of inner product W comma V, which is equal to 0. Now let us take one example for orthogonal complement. So the question is find the basis for W perp, where W is equal to span of, there are two vectors they have given, that is, let me consider it as W1 and W2. Okay, so we have, what is the formula for orthogonal complement? It is inner product of W comma V should be equal to 0. Now how to solve this? Okay, we have to find the basis for this W perp, and then using these two vectors we have to show that they are orthogonal complement. So let me take, say, v is equal to some vector x1, x2, x3, x4, and we will try to multiply v with the both terms w1 and w2. So what we will get, it is x1, x2, x3, x4 into, it is what, 1 minus 5, 2, 3 is equal to 0. That is the normal w inner product of dot products we are finding. Similarly, I am finding for the second vector x1, x2, x3, x4 with the second vector is equal to 0. Now I will write the direct equation instead of solving them, which is nothing but x1 minus 5 times x2 plus 2 times x3 plus 3 times x4 is equal to 0. Then similarly for the second vector, I am writing the same thing. So it is x2 plus 3 plus x4 is equal to 0. Now we have to do what? You have to write the augmented matrix. Okay, we have to reduce it, we have to try to reduce it. So it is what, 1 minus 5, 2, 3 given 0, 2 2 1 1 1 0. Okay, we have seen all the how to solve it, we know it, right? I'll directly apply the second row form, that is reducing the second row. R2 changes to R2 minus 2 times R1. It is what you will get. First row remains as it is, so second row will be 0, 11, minus 3, minus 5, 0. All right, now I will write the second row, I will write directly because we have already reduced. It is 1 and 0 now, we can reduce it directly. So the second equation will be what, 11 x2 minus 3 times x3 plus 5 times x4 is equal to 0. You have known about the pivot and the free variables already in the previous videos. So I will not go deeply in that. You know it. I will consider you know it. Okay, so I'll write the equation for x2. I'll get the x2 as 3 by 11 times x3 plus 5 by 11 times x4. Let me take the equation as 2, and the equation I will take as 1. Okay, I'm directly writing it now. So x1 minus 5 times, now I will apply the x2 there. Okay, I will substitute 2 in 1. So what I will get, so it is nothing but I have applied plus 2 times x3 plus 3 times x4 is equal to 0. Okay, so let's simplify it. So it is x1 minus 15 by 11 times x3 plus minus 25 by 11 times x4 plus 2 times x3 plus 3 times x4 is equal to 0. Let's reduce it further. So it is x1 plus 7 by 11 times x3 plus 8 by 11 times x4 is equal to 0. Okay, so what is x1 then? I will bring all the terms to the right hand side. So I will get this equation. Now we will write the general solution. Okay, general solution. So when you write the general solution, you have to consider something called as S and T's, right? So we know that S and T's could be founded with x3 and x4. So x3 be S and x4 is equal to T. So if I take the equation, say v is equal to x1, x2, x3, x4, I will write it everything together now. What is x1? Minus 5 by 11 x3 plus minus 8 by 11 times x4. What is x2? x2 is what? Okay, here it is. So write that x2. Okay, yeah, x4. And x3 and x4 I'll write it as it is. So I have taken it as S and T. Now I will write the terms for S and the terms for T. So what is that? S is minus 5 by 11, 3 by 11, 0, 1, 0. What is T? Plus T into whatever the terms related to x4, that we are writing it together. Now we got the answer, and we have to write the basis for the W prep. What is basis? It is a set, right? Set of two vectors or two or more vectors. So I'm writing the basis for W prep, which is nothing but the vectors we got. Now how to check whether the answer is correct or no? We have to know that whether the answer we got is correct. What is the formula? W into V is equal to 0. What are the two vectors we got? Let me take it as V1 and V2. We already know what is W1 and W2. What I'll do only for the one term. You can do for all the rest of the terms to check. Okay, what is W1? 1 minus 5, 2, 3. We have to find V1 into W1. Multiply this term with the W1. So minus 5 plus 1 into 2 plus 0 into 3. So let me simplify. Minus 7 by 11 minus 15 by 11 plus 2. So it is 22 by 11 plus 2 So it is equal to 0, right? If you solve, if I'll try to solve it, so it is by 11. Yeah, you will get the answer as 0. So that's how you solve it. You can solve for other terms like v2 into w1. You can solve and check whether you are getting the answer as 0. So this is a whole problematic solution for orthogonal complement. Stay tuned for other videos. Thank you so much.